this video, I will discuss processes of ideal gas and solve problems with respect to the isometric process. So I will divide the discussion for the processes of ideal gas into a separate part, and we all know that we have several processes. Una na dyan itong isometric process. So we also have isobaric, isothermal, isentropic. We also have polytropic. So those processes of ideal gas. But I will divide my discussion of those per video. So we will concentrate in this video in isometric process. So let's go ahead. Problem number 1. A perfect gas has a value of R is equal to 58.8. So we have R. Let's write that down. We have R, so that is your specific gas constant, 58.8 foot-pound force per pound mass Rankine. And we have K is equal to 1.26. And sabi dito, if 20 BTU are added to 5 pounds of this gas. So we have Q, so that means 20 BTU of heat is added to this gas. And then you have the mass of the gas, which is 5 pounds. So sabi dito, at constant volume. So if volume is constant, then we're definitely talking about the isometric process. So, and then next, when the initial temperature is 90 degrees Fahrenheit. So we have T sub 1, 90. So to make it absolute, notice here I write capital T. So we will add 460, and that will be equal to 540 Rankine. So the question is, find the letter A, temperature 2, delta H, or the change in enthalpy, the change in entropy, the change in internal energy, and also the work for a non-flow process. So the first quantity here that we are going to solve is T sub 2. We can do that by utilizing the formula for heat. So for an isometric process, heat is equal to mc sub v delta T, T2 minus T1. Actually, heat is always mc delta T. But because this is an isometric process, so therefore the specific heat that you are going to utilize is C sub V, the specific heat for constant volume. Okay, so we will algebraically solve for T sub 2. So we have Q is equal to M C sub V T sub 2 minus M C sub V T sub 1. Therefore, T sub 2 would be equal to Q plus M C sub V T sub 1 all over M C sub V. Okay. Now we have our heat, we have our T sub 1. What we don't have here is our C sub V, which is the specific heat at constant volume. But we are also given R and K. So based from our given, we can solve C sub V using the formula R over K minus 1. So your R is equal to 58.8. That's in BTU per, that's in foot-pound force per pound mass Rankine. And then you have K, which is 1.26 minus 1. So that is 0.26. Okay. So notice guys that our R here is in foot-pound force per pound mass Rankine. Notice it's in foot-pound force, and this is BTU. So therefore, in order for the C sub V to be in BTU as well, because Q is BTU. So if you're going to multiply that, then in order to unify yung mga units, then we need to convert the foot-pound force to BTU. So to convert that, we simply have to divide 778. So let's calculate for our C sub V. Let's get our calculator. We have 58.8. Then divided by 0.26 times 778. Okay, so the answer is 0.291. 0.291 BTU per pound mass Rankine. So we are now ready to substitute to solve for T sub 2. Q, again 20 BTU plus you have 5 pound mass, and then 0.291 BTU per pound mass Rankine, and then 540 Rankine. So notice here, I will cancel yung mga units. Pound mass is cancelled, Rankine is cancelled, and we have BTU here. So BTU plus BTU. Okay, I hope that is clear. And then in the denominator, again we have 5 pounds times C sub V, so 0.291 BTU per pound mass Rankine. So sa denominator naman, class, you can cancel pound mass, and if you divide later on, you have BTU in your numerator, and in your denominator, you have BTU per Rankine. So BTU will be cancelled out, and the final unit would be in Rankines. So let's get our calculator, and let's input our given. So 20 plus, let's have a quantity, 20 plus, let me just repeat that, we have 20 plus 5 times 0.291 times 540. Okay? And then we divide that by the product of 5 times 0.291. So the answer for T sub 2 is 553.75. Rankine. Okay? So next, what is your delta H? Your change in enthalpy. So let's go to the next page. Delta H, whatever is the process, is always equal to mc sub p delta T, or mc sub p times T2 minus T1. Okay? So again, from our given, we have K, and we have just solved for C sub V. So what we can do to solve for C sub P is to utilize the formula. K is equal to Cp over Cv, and then therefore C sub P is equal to K times C sub V. So we can substitute that to our formula. We have mass times K times C sub V, and then you have your T2 minus T1. We have already solved for T sub 2. Okay, so mass is 5 pounds, K is 1.26, C sub V is 0.291 BTU per pound mass Rankine, and then T sub 2 is equal to 553.75. T sub 1 is 540. So this is in Rankine. So let's check the units. Kung ano yung mga cancel, pound mass cancels out, Rankine cancels out, and the final unit is in BTU. Okay? So let's get our calculators again. Sabayan nyo rin ako. You can also get your calculator and calculate. So we have 5 times 1.26 times 0.291 times the quantity. We have 553.75 minus 540. So the answer is 25.21 BTU. So we have delta H, or the change in enthalpy, is equal to, again, 25.21. 25.21 BTU. Okay? So what else? We are also, so let's check this one. We have T sub 2 check, delta H check. How about delta S? So the change of entropy, I will discuss the formula. The change of entropy has a general formula of mc, and then integral of differential T over T. So we know that differential T over T is equal to the natural logarithm, no? So let's say we're talking about 0.1 to 0.2, so therefore this will now become mc and then the natural logarithm of t2 over t1. So since we are talking about the isometric process, and then therefore your C, your specific heat, will be C sub V. So ln T2 over T1. So this is just a matter of substitution again. We have 5 pounds, and then C sub V is 0.291 BTU per pound mass Rankine, and then ln of 553.75 divided by 540. Okay, so let's just draw a line there. So we have delta S is equal to, so again, let's get your scientific calculators and calculate with me. We have 5 times 0.291, so then times the ratio of 553.75 divided by 540. Okay, let me revise. So we have 5 times 0.291, and then times, let's 553, put a quantity 0.75 divided by 540. But before we do that, we will get the logarithm. Okay, so we have 1.455, and then the natural logarithm of the ratio of T2 over T1. Okay, so heat equals, the answer for delta S is equal to 0.0367. So the unit here, so we cancel out pound mass. So the unit for delta S, or the change in entropy, is equal to 0.0367 BTU per Rankine. So that is the unit, BTU per Rankine. Okay. Next, so let's check delta S, delta U. So delta U, the formula for delta U is always mcv delta T, whatever is the process. Delta U is equal to m c sub v delta T, T2 minus T1. But if you are observing, in the first part of the discussion, I used the formula Q is equal to mcv delta T. Okay? So Q is equal to mcv delta T. So I don't actually need to solve for delta U, because from these two formulas, I can already conclude that your delta U is equal to Q, and since Q is equal to 20 BTU, then therefore, my delta U is equal to 20 BTU. Okay, so the last part is letter B. What is the work for a non-flow process? Okay, so the general formula for the work for a non-flow process is always equal to the integral of your pressure times your differential volume from point 1 to point 2. Okay, but since we are talking about the isometric process and volume is constant, then therefore that integral is equal to 0. So the work for a non-flow process is always equal to 0. So in this problem, the work for a non-flow process is also equal to 0. Okay, so let's go to problem number 2. So we have a reversible non-flow constant volume process, decreases the internal energy by 316.5 kilojoule. So let's write the given. As we read, we have delta U is equal to negative 316.5 kilojoule. And we have the mass here, which is equal to 2.268 kilograms. And we also given the R, the specific gas constant. We have 430 joule per kilogram Kelvin. But for simplicity's sake, let's just make this 0.43 and make it kilojoule per kilogram Kelvin. So what we did there is we simply divide 1000 and obtain kilojoule. Just remember, 1000 kilojoules, 1000 joules is of course 1 kilojoule. Okay, and then we're also given the K, the ratio of specific heats, so 1.35. So we have to determine the work, the heat, and the change of entropy if the initial temperature is equal to 204.4. So let's go ahead and get the absolute temperature. So we have 204.4 plus 273. So 204.4 plus 273. We have 477.4. 477.4 Kelvin. So let's go ahead and go to our main solution. We have the work. From the previous problem, we have already concluded that the non-flow work for an isometric process is equal to 0, and this is from the given. It says here non-flow, reversible non-flow, so we're talking about non-flow work. So that's equal to 0. Letter B, we have heat, and from the previous problem as well, we have seen that your delta U is equal to your Q, and since delta U here is already given and it's equal to negative 316.5 kilojoule, then therefore Q, our heat, is also equal to negative 316.5 kilojoule. So the only thing left here is to solve for the change of entropy. So the change of entropy, delta S, is equal to mc sub v. We have also derived this formula in the previous problem. The natural logarithm of T2 over T1. We don't have our T sub 2 yet, but we already have our T sub 1. So let's solve for T sub 2, and we can use delta U is equal to mc sub v, then T2 minus T1, T2 minus T sub 1, and from the previous video again, we have already solved for T sub 2, and that is equal to delta U plus mcv T sub 1 over mc sub v. Okay, so let's go here. We have T2 is equal to delta U is equal to negative 316.5 kilojoule. Then we have plus mcv T sub 1 plus mass 2. Let me just check, 2.268 kilograms, and then your C sub V. Okay, so C sub V we haven't also obtained that, but that's very easy to solve. C sub V is equal to R over K minus 1, R over K minus 1, so our R is 0.43 over K minus 1, so this is 0.35. So we have 0.43 divided by 0.35. So the answer is 1.23. 1.23 kilojoule per kilogram Kelvin. So 1.23 kilojoule per kilogram Kelvin. Then from the formula, we multiply T sub 1 and it's equal to 477.4. 477.4 Kelvin. Then divided by mcv. So m is 2.268 kilogram times cv 1.23 kilojoule per kilogram Kelvin. So let's get our calculator and solve for T sub 2. So we have 316.5 negative 316.5 plus the quantity 2.268 times 1.23 times 477.4. Then let's divide that by 2.268 times 1.23. Okay, so the answer for our T sub 2 is 363.94. T sub 2 is 363.94 Kelvin. So we can go ahead with our delta S. It's equal to mcv. I have already written that down, mcv and then ln of T2 over T1. So m is 2.268 kilogram, Cv is 1.23 kilojoule per kilogram Kelvin. Then the natural logarithm of 363.94 over 477.4. So again, let's get our calculator here. And you can also get your calculator, and it's best if you will calculate this with me. So we first do the ratio of the temperature is 363.94 divided by 477.4. Then after obtaining that, let's get the natural logarithm, and then we multiply that by, let's check. Okay, so I see here that to calculate, I made a mistake. So let's calculate it. We have 363.94 divided by 477.4, and let's get the natural logarithm of that, and let's multiply it to 1.23 times 2.268. So the answer is negative 0.757. Negative 757. So the unit is kilojoule per Kelvin. Okay. So let's go to our last problem for this topic. So problem number 3. We have 10 cubic foot vessel of hydrogen at a pressure of 300 psia is vigorously steered by paddles until the pressure becomes 400 psia. So here, because the problem uses the word vessel, then this means that this is an isometric process. And the volume, you can assume that the volume did not change. We have volume is equal to 10 cubic feet, and we have P1 is equal to 305 psia. We have P2 is equal to 400 psia. We have to determine the change in internal energy and also the work. So it's also noted here that no heat is added, and it's also given the specific gas constant and the specific heat for constant volume for hydrogen. So you can also write this Q is equal to 0, but it doesn't mean that your delta U is already equal to 0, because we have the change in pressure, and therefore we can assume that there's also a change in temperature. So following the isometric rule, right? Isometric process, wherein if your volume is constant, then therefore you will have a change in pressure and temperature. So we have delta U is equal to mcv times quantity T2 minus T1. Although we are not given the temperature, from the perfect gas law, we have PV is equal to mRT, and then therefore T is equal to PV over mR. So if we will substitute that value of T to our delta U, then we will have mcv. T2 is now T2V2 over mR, and then minus T1, so it was T1V1 over mR. So delta U is equal to, we will factor out mR, we'll have Cv over mR, and then T2V2 minus T1V1. So we can cancel out the mass. But in this case, volume is constant, so we can factor out the volume. So V is equal to V times the quantity P2 minus P1 all over R. So that would be the formula, the working formula that we will use to solve for the internal energy. So we're given the C sub V, we're given the volume, we're also given the temperature and the R. So we can go ahead and put our given and solve for delta U. So we have C sub V, so it's equal to 2.434 BTU per pound mass Rankine. And then we have V, this is 10 cubic feet. And we have the difference in pressure. Take note that PSIA is pounds per square inch. So therefore, we need to change this to PSF, pounds per square foot. Okay? So if we get the difference of them first, 400 minus 305, we will multiply that by 144. For our unit here to become pounds per square foot. And then R is equal to 0.985 BTU per pound mass Rankine. Okay, so let's check out the cancellation of units first. So BTU per pound mass Rankine, lahat yan cancel. Then we have here square foot is also cancelled. And the final unit is pound force. This is pound force feet. So since that is in pound force feet, then we will simply divide the answer by 778 in order to obtain BTU. So let's get our calculator. So we have 2.434 times 10 times 400 minus 305, so that is 95, and then times 144. And then let's divide that by 0.985 times 778. And the answer that we will get is 434.5. So we have delta U is equal to 434.5 BTU. Now, the next unknown in this problem is our work. Okay, so this problem is a bit peculiar because as I've stated in the previous two problems, the non-flow work is equal to 0 for an isometric process. But there's another formula that is used to solve for the non-flow work, and that is equal to Q plus Q is equal to delta U plus your non-flow work. No? Since in the previous problems, Q and delta U are equivalent, so therefore your non-flow work will be 0. But in this problem, your Q and your delta U is are not equal quantities. It says in the problem that your Q is 0 because no heat is added. So therefore, your Q and delta U is not equal in this specific case. So we can substitute Q by 0, and therefore our non-flow work would be equal to our negative delta U. So our non-flow work is now equal to negative 434.5 BTU. Okay, so that's it for our discussion for problems regarding isometric process. I hope you have learned something. Thank you for watching.